So based on the type of diagram that we get or the type of information we get, we're going to be able to create a quadratic equation that kind of models that information. So today is modeling with quadratic equations. So we're going to look at these different types of information. So we're going to see information whenever we're given in a word problem, whenever we are given it in a graph, and whenever we're given it on a table. And based on this, we're going to be able to create quadratic equations. And so the steps that we're going to take, the first thing we're going to do is we're going to analyze the information, see what we're given, see what we need to model to begin with. Then we're going to determine the constants in the quadratic equation. So basically, what are the things that affect the x and the y's? Then we're going to write the quadratic equation that models the situation. Basically, write the quadratic equation in the standard form: ax squared plus bx plus c. And then we're going to actually solve if we're asked to solve for something. And then we're going to choose a method to do that, whether it's factoring, whether it's putting it in the quadratic form, or whether it's completing the square, whatever our preference is, we're going to choose a method to solve that. So that's basically what we're going to see today. So here we have a word problem, and it says a quarterback throws a football to a teammate. The football is 6.5 feet above the ground when it leaves the quarterback's hand. His team catches it 3.5 seconds later at a height above the ground of 5 feet. Okay, so what we're going to use here is we're going to use an equation, and you don't have to remember this equation, but I'm going to give it to you. And this is the equation that we're going to use as our starting point. We're going to use the projectile motion formula, which basically tells us that our height is equal to negative 16 t squared plus vt plus HL. So again, you don't have to memorize this. But what we're now going to do is we're going to analyze the information we are given. What does this word problem tell us? Well, it tells us that when the football is 6.5 feet as soon as it leaves the quarterback's hand. And then 3.5 seconds later, it's 5 feet above the ground. So that means that our initial height, as soon as the quarterback releases it, our initial height, our height at 0 seconds is 6.5 feet. And our height at 3.5 seconds later is 5 feet. Okay. And so what we're given here is information about our initial height and our height at 3.5 feet. The information that we're not given is information about our velocity. And what you'll see is that in our projectile motion formula, we need to know our velocity. We need to know our v in order to solve. So what we want to do is we want to identify our v. The way that we go ahead and identify our v will represent the initial velocity first before we can write the quadratic equation. So we need to identify this constant. Our constant will be our v, which can help us model this quadratic equation. Okay, so how are we going to do that? Well, basically, we're going to take this equation and we're going to go ahead and plug in the information that we know. More specifically, I'm going to use this information and plug that in. So basically, my height after 3.5 seconds, is 5. Negative 16. My time is 3.5. And I'm looking for my v. My time again is 3.5. And my HO, my initial height, is 6.5. Oops. So basically what I've done here is I plugged in information that has been given to me. More specifically, information about what my height is after 3.5 seconds, because that will help me solve for my v. So I need to solve for my v in order to create an accurate quadratic equation that models this situation. So basically, we're just going to go ahead and solve for those things that we can solve for. Right, so right now I'm just trying to isolate that V. And by doing that, I see that V is equal to approximately 56. Okay, so what I did here was I solved for this. I put this into the calculator. That was negative 196. Then what I did was I combined it, negative 196 with 65, which gives me negative 189.5. Then what I did was move 198.5 over to the other side. So I added 5 to it. Or no, I moved this, so I added 189.5 to my 5, which gave me 194.5. And then I solved for my V. So I just divided on both sides and solved for my V. And so now my V is 56. So now what this allows me to do is create a formula, a quadratic formula that will model this situation and allow me to find the height at any moment in time. So basically, I'm going to go back and plug in my V. Now that I know my V, I can plug it in. And I'll go ahead and show you here. So my height will be equal to negative 16, whatever time it is, plus 56, because that's my velocity. We found out that V is 56, T, and then my HO that I'm given is 6.5. And so this is my quadratic model, which models the situation. Now what I can do with this information is I can find what the height is at any moment in time. Okay? So in order to create a quadratic equation that models a situation, what I need to do is I need to take my information given, identify what my constant is. This is my constant. And because I'm not given that constant, I need to solve for it. So that's what I did here. So solve for that constant. And once I do that, I can then go ahead and create a quadratic equation that models this situation. Okay. Any questions about what I did here? And we'll go over some more examples, but any questions right now?
No, ma'am.
Okay. Where am I? Oh, and then this is what we looked for. We looked for that velocity, which was equal to 56. And then what was our quadratic equation that modeled this situation? Again, was just so you can see it clear. So we identified our velocity, our constant, and then plugged that back into the quadratic equation. Now what we can go ahead and do is based on this, we can solve many different things. Now that we have our quadratic equation, we can solve a lot of different things. So this one says the model, now here it's given us that quadratic equation we looked for. And based on that, what we're asked to do is we're asked to find out what is the maximum height the ball reaches. Okay, so we have our quadratic equation. This is the one that we just created, so it's nothing new. Except here, x replaces t, just so it's easier for us to work with. It's in quadratic form, but it's the same thing. Okay, so now we have our quadratic equation, and we're looking for what is the maximum height that this ball reaches. Well, think about if we were to throw a ball, this would represent our maximum height. Our maximum height is halfway all the way up as it is all the way down. And so if we were to graph this, what it would represent is our axis of symmetry. What it would also represent is, because we're looking for what is the maximum height, we're looking for our y values. Our y values represent our height, while x values represent our time. And so because we're looking for our maximum height, what we're going to look for here is our y-intercept. Okay, but what we need to do is identify the x value of our y-intercept. And so what we're going to do is we're going to find the axis of symmetry, which basically uses this equation right here. Okay, and just a reminder that this is A, this is B, and this is in standard form. This is A, this is B, and this is C of my standard form. So that's what I'm plugging in. So B is 56 to negative 16. That's what I'm solving. And then simplified, that's approximately 7.4, which is approximately 1.75. Okay, so this is the x value of my axis of symmetry. But what I need to identify is my y value. This is the time in which I will have my maximum height, but what I'm looking for is my height of my maximum height. And so I'm looking for my y. And so the way I'm going to look for my y is I'm just going to plug that x into my equation. So negative 16, 1.75 squared plus 56, 1.75 plus 6.5. Okay, and that will allow me to solve for my y of my maximum height. Okay, so I'm plugging that in, putting this into my calculator, adding all those together, and what I get is it's equal to 55.5 feet. So this is telling me that my maximum height is 55.5 feet. Okay, so what are we doing here? Well, we already found our quadratic equation. Well, using this quadratic equation, we can find different information about what the situation is. And so what we're trying to find is, what is the maximum height the ball reaches? Well, if we were to see the ball being thrown on a coordinate grid, what we'll notice is that the maximum height, the highest point that the ball reaches, occurs where the axis of symmetry is. So basically, the point at which that height or that loop is symmetrical. So the point at the axis of symmetry will tell me at what time do I reach my maximum height. But in order to find my y, my maximum height, what I need to identify first is that number of time. What is my x? What is my x in my axis of symmetry? And so that's why we use this equation right here. This allows us to find out that at 1.75 seconds, I reach my maximum height. Okay, and that's what I can use to plug into my quadratic equation to solve for what actual height am I at 1.75 seconds. And so that's what I'm doing here. I plugged in my x of my axis of symmetry into my original equation, and that's when I see that my y is equal to 55.5 feet. But that is my maximum height. Okay. Another way that you can go ahead and solve this, if you do have a graphing calculator, is you plug in this quadratic equation into your graph. And what you're looking for is your vertex. What is the point of your vertex? What is your maximum height? Okay, give me 1 second. See if my graphing calculator allows me to look at this. Okay, yeah, it does. Okay, let me show you. So what we're looking at, if we were graphing this quadratic equation, is we're looking at this point right here. And it's not 100% clear because it is a very large graph. What we're looking for is here, this maximum point, this vertex point, and I can zoom in. So that maximum point right there is going to represent our maximum height, right? That's the highest height that we can reach. And so if I had a graphing calculator, what I'd be able to do is I'd be able to plug in my quadratic equation. I'm trying to get it back to where it showed me what. Okay. So I plug in my quadratic equation, and if I point right at that vertex, you'll see that it gives me the same information. My x is 1.75. So at time, 1 second, I think, 1.75. My height, my maximum height is 55.5. So this might be easier for some of you, but in order to do this, you would have to use a graphing calculator, but basically doing the process that we just did would give you the same exact answer. Okay. Any questions about what we did here? Okay.
No.
Okay, then let me go back. And that's not it. Okay. So now we're going to look at one more type of thing that we can solve with this same equation that we're working with. Actually, this one's a little bit different. So in this type of problem, we're given a quadratic equation. So y equals negative 16x squared plus 35x plus 65. So it's a little bit different. And it says, this model describes the height y and v of the football x seconds after it is thrown. If the ball is not caught, how long will it be in the air? So in this instance, what we're looking for is I'm going to draw kind of a representation of my coordinate grid. And what I'm looking for is how long, if the ball is not caught, how long will it be in the air? So I'm looking for, in this instance, time. Not looking for height, I'm looking for time. This is time, this is height. And what I'm looking for is if my ball was thrown, how long would it be in the air before it actually hit the ground? That's my representation of ground. And the reason it starts up here is because remember that in our original equation, the height at our initial height was 6.5. Okay, so what I'm looking for is how long will it be in the air if it's never caught? So once it hits the ground, how long will it have been in the air? Well, what you'll notice is that point that represents how long it'll be in the air represents our x-intercept, where our model crosses the x-axis. So what we're going to look for here is what is our time when our height is officially equal to 0 when it hits that ground. Okay, and so the way that we're going to solve this is we can actually do this in two ways. So because we're looking for our x-intercept, what we're looking for are our zeros. Our zeros represent when our graph hits the x-intercept. So we're zeros. So we've looked at our zeros the past couple of weeks, and we've discovered that there's many ways to go about solving this. We could factor it out, we could complete the square, or we could use the quadratic formula. My favorite and possibly the easiest is just using the quadratic formula. So using the quadratic formula will give me my zeros, which are my x-intercepts. So once again, this is my A, this is my B, this is my C. And I'll change the color so we can see this go in. And so I'm plugging this into my quadratic formula. Let me model it real quick. Okay. And 2. Okay. So the first one is my B's go in. So my B is 35. Okay. Now my A's go in. negative 16, negative 16, and then my c goes in. And so what I'm doing here is I'm putting this equation into the quadratic formula because that will give me my zeros, my x-intercepts. And when I do that, I'll identify that my x's are at, I have two x's because I do plus and minus. So I have one x at negative 0.2 and I have another x at 2.4. Well, what I'll notice is I cannot have negative time, right? I can't start to identify what my height is even before I throw that football. And so I can't have negative time. And so that leaves me with this x. And so that x would tell me how long it takes before the ball hits the ground, or how long it'll take for the ball to hit the ground if it is never caught. So what the time is whenever the height is 0. And then once again, this is because it does not make sense to have a negative time as the ball cannot hit the ground before it's even thrown. And so our x here, our x-intercept is 2.4. That's how long the ball is in the air before it hits the ground. Okay, and so that is modeling with a word problem. Now we're going to look at modeling when we have a table. And so here again, we are given some information about this table. Basically, this equation models the distance it takes a car to stop, can be modeled by this function that we see here, where d represents the stopping distance in feet, v represents the initial velocity in miles per hour, and f represents a constant function to friction. And we have some information about the data, how our v's and d's are related. But what we'll notice is we're not actually given any information about our f. We're told here that f is our constant. We're not told exactly what that f is. And so once again, we run into this issue where we're not given our constant, and we need to find our constant in order to write a quadratic equation for this table. So I need to identify what my f is. The way that I'll identify my f is I'll choose one point on the table. I'll choose these, and this is what I'll plug in order to solve for my f. So my d is 38 is equal to, my v is 20. And so what I'm doing here is I'm looking for my f, because I need to know that constant in order to use this equation to solve for anything else. So how do I do this? It takes up 67.4, multiply on both sides, allows me to cross that out. That's 67.4. Oh. So I'm going to have 64.4 times 38 is now equal to, oh, I need to move that. Sorry, didn't put that in. Okay. It's now equal to, I can solve for that. I can solve for that side now. I'm going to try to keep this. Now I'm trying to solve for my f. This is equal to 160. Now I need to further isolate my f, so I'm going to divide by 38 on both sides. Equals, I am at 22.616. Okay, now I need to further isolate my f. And what I'll see there is my f is now equal to approximately 0.35. So now that my f is approximately 0.35, that's what I can plug into my equation. So my new equation will be df dv is equal to 2.15 v squared 22.54, because now I'm actually going ahead and I'm multiplying it by the 64.4. And so this will be my equation, which will more accurately represent what's going on here. What is my situation? What it's representing my model. So whenever I'm given information, I need to identify my constant in order to get a quadratic equation which will represent my model. And so this is that quadratic equation that represents my model. And I got that after I found my constant which is f. Okay. Where am I? So now I have that equation right here. And now that I can use that equation to answer different questions. So now I'm looking for, it takes a car driving in the rain 261 feet to stop. What was the car's initial velocity when the driver started to brake? So now I'm looking for v, my initial velocity. So now I'm looking for my v. So I start here. I'm going to write down that equation just so we can work with it. And what this tells me is it takes a driver in the rain 261 feet to stop. So my distance is 261 feet. And so now what I'm going to do is look for my v. So basically I'm just isolating my v to find my v. What is my velocity when my distance is 261 feet? So cancel this out, divide, multiply on both sides. I need to further isolate my v, so I'm going to divide by 215. That'll give me approximately 2,736.25 is equal to v squared. To get rid of my squared, I have to take my square root of both sides. And that will give me approximately 52. So that means that my initial velocity is about 52 miles per hour. Okay, so given my quadratic model, I can use that quadratic model to solve the equation, which in this instance is going to be my initial velocity. I'm going to solve for my velocity when my distance is 261 feet. And so by doing that, I'll identify that my velocity is 52. Okay. So now we're going to see this when it happens in graphs. So basically, you're just doing the same thing. You're using the information you're given. You're analyzing that graph, and what you're looking for is the constant. So you need to find the constant, and that constant will help you create a quadratic model that will actually help you solve questions based on the information that you're given. So here you're told the main cable of a suspension bridge forms a parabola described by the equation, and we're given an equation where y is the height in feet of the cable above the railroad, and x is the horizontal distance in the feet from the left bridge support, and a is a constant. So a is our constant. So we're more than likely going to have to solve for that constant in this part of the equation. The vertex of the parabola is hk, which represents the minimum height of the cable. So h, we're told here, hk represents the minimum height. This is our minimum height. right? Because that's the lowest our line goes. And so it's telling us that that represents our H and that represents our K. H is 50, K is 6. And so what we'll notice is we are given this equation to work with. So y is equal to a k minus h squared plus k. And what this tells us is that our h and k and our h and k are given. So our h is 50 and our k is 6. What we need to know in order to create a quadratic model, a quadratic equation that represents this model, is we need to identify our a. And so once again, we're going to have to identify the constant. We're going to have to identify what a is. And the way that we're going to do that is we're going to choose a point on this graph. So I'll choose this one, and that's where we're plugging in to solve our a. So this is telling me my x is 30 and my y is 7.92. So I'm going to erase this just so we have more space. So y is 7.92. I'm looking for my a. My x is 30. And then my constants were 50 and 6. So now what I'm going to do is I'm going to use this information to solve for my a. Because I need to know that constant in order to create a quadratic model which will model this situation. Okay? So goes a, and then get to 22 plus 6. So I'm looking for my a. 7.92 equals a. This is now 40 plus 6. Subtract 6 from both sides. 1.92 equals 40. A, divide by 40 on both sides to find my a. A is now equal to 0.0048. So now that I have my a, I can plug my a back into my original equation because a will represent my constant. And so plugging it back into my original equation gives me y is equal to a, which is 0.0048, x minus 50, which is my h, plus k, which is 6. Okay, so again, with all of these different types, what we need to look for is our constants. And once we identify our constant, we can find an equation which will accurately model this situation and allow us to plug in information or solve for a specific question that we're being asked. And so we'll look at an example question right now. Give me one second. Okay, sorry. Okay, so now that we have that equation, is just represented right here. Now what we can do with that equation is actually solve or answer a problem. So this one asks, at what height above the railroad does the cable attach to the left support? Whenever the cable attaches to the left support, my x will be 0. And so basically I'm looking for my y. What is my y when my x is 0? So basically I'm just plugging in 0 for my x. To find my y, my height, whenever that cable attaches to the left support. Now I just solve for this. Which gives me about 12, 6, which gives me 18. So basically what this is telling me is the cable attaches to the left support. Why am I spelling cable like that? The cable attaches to the left support. At 18 feet. Okay. So what are we doing? So basically what we went over were real world situations can be presented in different ways, a verbal description, a table, or a graph. And we've worked with all these different ways today. And basically, once we get a quadratic model that represents these situations, we can go ahead and find our zeros. We can find information about our vertex, which represents our maximum height or maximum. And we can even solve information about our y-intercept. So basically, once we are able to map these real world situations using a quadratic equations, we can go ahead and solve problems using that information. But in order to do that, the first thing we need to do is analyze the information we are given, whether it's a verbal description, a table, or a graph. We need to determine the constants, because once we determine the constants, we can then write a quadratic equation that models that situation. And then lastly, we can solve for whatever type of problem we are given. And we can solve using many different ways. We can determine the square root, we can complete the square, we can factor, or we can use a quadratic equation. So throughout today, basically, we took information given. We solved for the constants. Solving the constants allowed us to write quadratic equations. And those quadratic equations allowed us to solve problems. Okay. But like always, we'll go over some more practice problems tomorrow. But are there any questions right now? Questions?
No, miss.
Okay. If there's no other questions, I will see you guys tomorrow. Bye, guys.
Bye, miss.
Bye.